there. Today we're going to be graphing square root and cube root functions. This is related to the chapter we're in because we know that we've been dealing with rational exponents. And so if we know how to graph things like x squared, but what if we have x to the 1/2? Well, x to the 1/2 is really like the square root of x. What if we had x to the 1/3? Well, that's really like the cube root of x. So that's kind of how these are related to this chapter, since we're dealing with these rational exponents. So today we're going to be talking about the following things. I can graph square root and cube root functions. We're also going to talk about the domain and range of square root and cube root functions. And we're going to describe the transformations of the corresponding parent function. And those are the same transformations that we've done the whole time. So when we talk about radical functions, the radical functions we're going to be dealing with are in this form. They're going to be in the form y equals a times the square root of x minus h plus k, and y equals a times the cube root of x minus h plus k. So our friends a, h, and k are back, and they have the same things that they did before. The thing is that we're going to have to look at what these new parent functions look like. So let's talk about what those parent functions would look like here. So the parent function for the family of square root functions is f of x equals the square root of x. So let's think about the domain for this function. The domain is not all real numbers, because the domain talks about the values that you can put in for x. You cannot take square roots of negatives, so we can't have any negatives. The first number that we're able to take the square root of is 0. So our domain here is really x is greater than or equal to 0. And if you wanted to write it in interval notation, you could. I'm okay with that. And so then what would the range be? Well, maybe we should have a table of values, and maybe the table would help us with that range. So maybe let's find a table of values. And because this is the domain of the function, we're not going to bother putting any negatives in. So we'd start with 0. And oftentimes then we'll plug in like 0, 1, and 2. The problem is if I put 2 in, I'm taking the square root of 2, which I don't know what that is off the top of my head. But what's a number that's easy to take the square root of? Well, 4 is a number that's easy to take the square root of. What's the next number that's easy to take the square root of? 9. So maybe we could use numbers like this instead. So let's take the square root of 0, that's 0. The square root of 1, 1. The square root of 4, 2. The square root of 9, 3. That's how easy the table should be, always, okay? It should be super easy to do that table. And so what do you notice about all of the y values? Well, I noticed that we started at 0 and we're getting larger. And when we think about the domain, that makes sense, because the smallest value that we can take the square root of is 0, and then everything else is going to increase. And the square root of 0 is 0. So our range is also y is greater than or equal to 0. So if we plot those points, let's see what that looks like. 0, 0, 1, 1, 4, 2, and then for 9, 3 would be off my paper, would be over here. And again, we don't put arrows on both sides, because remember, we couldn't take the square root of anything here. So that's what our square root function looks like. And notice that it looks like half a parabola tilted on its side. Not just tilted on its side, but it's as if the x and y values were switched, right? And that's because the square root is the inverse function of the quadratic family that we studied. But notice that we had to only have part of it so that this could be a function too. But anyway, that's what the square root function looks like. And let's make a little rule that any time that we graph square root functions, let's So for square root functions, let's always use 0, 1, 4, and 9 for x. It'll make our lives so much easier if we always use those values, because those are easily square rootable since they're perfect squares. Well, let's think about the cube root function. Does this have a domain restriction? Well, the square root, we were not able to take the square root of negatives, but cube roots, we are able to take the cube root of negatives. We can take the cube root of any number. So the domain doesn't have any restrictions to it. And because in this case we can take the cube root of anything we want, the range is also going to be anything we want. So our domain and range are all real numbers for cube root functions. But what is the shape of that cube root function? Well, let's maybe make a table to find out. Now we said that we were able to take negatives, and so a lot of times we would use -2, -1, 0, 1, and 2. But if I put -2 in, I'd be taking the cube root of -2, and I don't know what that is off the top of my head. Let's see if these other numbers would work. -1, can we take the cube root of -1? We can. The cube root of -1 is -1. What about the cube root of 0? That's 0. And the cube root of 1 is 1. So those numbers work, but I don't like this 2 and -2. Is there another number that might be easy to take the cube root of that's not too far off the graph? Well, what about 8? We could take the cube root of 8, and that's 2. Likewise, over here on the negative side, we could maybe take the cube root of -8, and that would give us -2. So let's see what happens when we graph those. 1, 2, 3, 4, 5, 6, 7, 8, -2. So that's down here on my table. -1 is here. 0, 0, 1, 1, and then 8, 2 maybe would be up here. And notice that I am going to connect these in both directions. And it doesn't keep going up this, I mean it does keep going up that way, but notice that it is almost like longer than it is taller. So it is getting bigger to the right and smaller to the left. But notice it doesn't curve up like this, that again it's slowly but surely going there. And you can see there's no endpoints, and that's why we have the domain and range that we do. And so why don't we, for cube root functions, why don't we always use those values? Let's say that we're always going to use -8, -1, 0, 1, and 8 for x when we have cube root functions. I bet that's going to make our life a lot easier. So now that we've got an idea of the shape of the parent functions, something that starts and goes in one direction for the square root and something that's pulled in both directions for the cube root, let's do some, put some A, B's, and Q's in there and see what we get. Example 1 wants us to graph y equals 1/2 times the square root of x, and then also state the domain and range. And we'll also take a minute to compare the function with the parent function. So because this is a square root function, we know that we're going to use the numbers 0, 1, 4, and 9. And when we use those numbers, we're also going to deal with the a value in our table. So this is actually, we're going to substitute these values in, but also include the 1/2. So this is essentially 1/2 times the square root of 0. Well, that's 0 times 1/2 is 0. Next, I have 1/2 times the square root of 1. Well, the square root of 1 is 1 times 1/2 is 1/2. Now I have 1/2 times the square root of 4. Well, the square root of 4 is 2. 2 times 1/2 is 1. Now let's put 9 in. 1/2 times the square root of 9. The square root of 9 is 3 times half is 3 over 2, or 1 1/2. And so then we can plot those values, 0, 0, 1 1/2, 4, 1, 9 3/2 is over here. And we can connect them with a slightly curved shape. So we have an endpoint here at 0, 0, and this one goes up to the right. So what is our domain? Our domain still, notice, started at 0 and went to the right. So our domain is x is greater than or equal to 0. What about our range? Notice our range, we started at 0 and we're going up. So our range is y is greater than or equal to 0. So the same domain and range as the parent function so far. But it is a little different from the parent function, isn't it? You don't have to graph this, but if I were to graph the parent function on here, this is what the parent function would look like. Do you notice that it is the same shape except it's shrunk a little bit vertically? And when we look at our coefficient, our a value is less than 1. And that a value that's less than 1 tells us that there should be a vertical shrink. So everything is kind of confirming itself. The fact that the a value is, the absolute value of a is less than 1, and the fact that it does look shrunk here from the original function kind of confirms that it is a vertical shrink. Okay. And that's it. That's example 1. Let's try example 2. This says graph y equals -2 times x to the 1/2. Well, what the heck is that about? Oh yeah, when I have x to the 1/2, remember that this is really the same as the square root of x. Now, careful, do not put the -2 under the radical. It is only the x that's being raised to the 1/2, so we only put the x under the radical. But we are doing a square root, oops, and since we're doing square root, let's use our friends 0, 1, 4, and 9. And let's find out what our values are here. So if I put 0 in for x, I have -2 times the square root of 0. Well, that's 0. I have -2 times the square root of 1. Well, that's 1 times -2, which is -2. I have -2 times the square root of 4. And that's 2 times -2 is -4. And -2 times the square root of 9. So that's 3 times -2 is -6. So let's look at these guys, about where they end up. So I have 0, 0, 1, -2, 2, 3, 4, -4, and then 9, -6 would be down here somewhere, okay. So if I connect them, notice I'm going in a different direction, aren't I? But I'm still starting here at the 0, 0. But this time notice that we're going down instead. We're still moving to the right in this problem, but we're going down instead. So how does that affect the domain and range? Remember, the domain, we look at our x values. And in our domain, we notice that we start at 0 and we go to the right. So our domain is still x is greater than or equal to 0. But let's look at our range. Our range, we start here, and we're not going up from 0. We're going down from 0. So our range is y is less than or equal to 0. So that's different from our other function. What is it about this function that we graph that you think makes it go less than or equal to 0? Well, if you said that -a value, you're right. It's that -a value that caused the, what is it? The reflection in the x-axis. And that's why instead of instead of going up, it's going downward instead. So let's take a look at that then and think about the comparison. Remember, we think about RST. Because A is negative, that does mean that there is a reflection in the x-axis. Again, we should say that it's in the x-axis because you can reflect over lots of different things. Our S, we might not be able to tell by looking at it, but we can look again at the equation at the absolute value of A, and we see that that's greater than 1, and so that means that there's a vertical stretch by a factor of 2. The T was the H and K, which are both 0 here, so we don't have any translation to deal with. Okay, so that's example 2. In example 3, it wants us to graph y equals negative 1/2 times x to the 1/3 and state the domain and range and then compare. Well, again, this negative 1/2 x to the 1/3 is really like negative 1/2 times the cube root of x. Again, it's only x that's being raised to the 1/3, so only put the x under the radical. And this time, you guys, we are not going to use 0, 1, 4, and 9 because we have the cube root. When we have the cube root, we're going to use negative 8, negative 1, 0, 1, and 8. And so let's find what these are. We're going to take negative 1/2 times the cube root of negative 8. Well, let's think. The cube root of negative 8 would be negative 2 times negative 1/2 would be positive 1. I have negative 1/2 times the cube root of negative 1. So the cube root of negative 1 is negative 1 times negative 1/2 is positive 1/2. Next, I have negative 1/2 times the cube root of 0. Cube root of 0 is 0 times anything is 0. So you can see how easy it is to substitute these in when you have those perfect cubes under there, isn't it? So next we're substituting in 1. The cube root of 1 is 1 times negative 1/2 is negative 1/2. Next we have negative 1/2 times the cube root of 8. The cube root of 8 is 2. 2 times negative 1/2 is negative 1. And we can substitute these values, or plot these points, sorry. 6, 7, 8, 1, 1, negative 1/2, 0, 0. So again, we just plot these points. Remember, the cube root function does extend in both directions. And when we look at the domain, then we can see that there isn't really any start or stop, that our domain is all real numbers. And that our range, even though it's not kind of growing as fast as the x values are, our range, because there are no boundaries there, our range is also going to be all real numbers. And we can compare just by looking at the parent function and seeing how it relates. Well, we have an a value that's negative 1/2. So that negative tells me that there is a reflection in the x-axis. The S is a vertical stretch or a shrink. And I look, and the absolute value of A is less than 1. So that tells me I'm going to have a vertical shrink. And T translation, any H or K's, we don't have anything there. And that's your graph. So example 4 is going to be similar. I'm going to kind of go quickly through this. We're dealing with the cube root of x. Cube root means we're going to use -8, -1, 0, 1, and 8 every time. And now we're going to substitute these different values in. I won't write this one out. So I'm going to take the cube root of -8, which is -2, times 2 is -4. Next, we'll put -1 in there. The cube root of -1 is -1 times 2 is -2. The cube root of 0 is 0 times 2 is 0. The cube root of 1 is 1 times 2 is +2. The cube root of 8 is 2 times 2 is +4. So we can plot those points. -8, -4, -1, -2, 0, 0, 1, 2, 8, 4 might be over here. And then I'm going to connect those. Notice this covered a little more of the graph that we get to see. I wonder why that is. So when we're looking at this, again, from left to right, we have arrows in both directions. Remember, you can take the cube root of anything. Lots of clues here to show us that our domain is all real numbers. And again, we have arrows both going up and down, so that means our range is also all real numbers. And for our comparison, we can take a look at the parent function and compare it to the new function. Notice that we have a 2 as an A value. What does that mean about a reflection? There isn't one. What about a vertical stretch or shrink? Well, that 2 is bigger than 1, so that tells me there's a vertical stretch. Maybe that's why it took up more of the graph that we saw. And then T is a translation, and again, we don't have any H and K yet, so that's that. So notice that even when we had an A value, it was really easy to make these tables when we chose those nice values. So then what if we throw H's and K's in there? And we knew that was coming. So what we're going to do is when we graph things with H and K, we are going to ignore the H and K in the table. This is like the biggest thing. Ignore H and K in the table. I promise we'll deal with them later. But don't worry about them, because if you do, then the tables are going to be a bigger pain to deal with. And so that's what we're going to do first. We're going to ignore H and K in the table, and then we're going to sketch the graph of, notice, the non-translated function. So we're going to include the A in the table, but not the H and the K. And then it's after that that we're going to be able to translate the graph H units horizontally and K units vertically, just like we did before. Okay? So let's talk then about to find the domain of a square root function. So to find this domain of a square root function, essentially, it's because our radical, the radicand, has to be greater than or equal to 0. So what we're going to do is set what's inside the radical greater than or equal to 0 and solve. This is our important piece here. We set what's inside the radical greater than or equal to 0, and we solve. Okay? Now, to find the range of a square root function, what we're going to do is look at the sign of A. Is A positive or is it negative? If it's positive, the graph's going to be going up. And if it's negative, that means that the graph's going to be going down. And what is it about the function that's moving it up and down? Well, it's that K value. So what happens is our range always deals, oh goodness, sorry. Our range always deals with k. Always, always, always deals with the k value, because that's the translation of the function from 0 either up or down that many units. So the domain, we deal with what's inside of the radical, and then the range, we always deal with k. And if a is positive, it's going up from k. If a is negative, it's going down from k. Now, one super nice thing about the cube root function, though, is that it doesn't matter if we've moved anything around. The domain of a cube root function is going to be all real numbers, regardless of if you move it left, right, up, and down, or whatever. Same thing with the range. The range of a cube root function is always just all real numbers. So really the only domain restrictions or issues that we have to think about are with those square root functions. So let's take this and let's apply it to a couple of different problems and see what we can do. Let's practice graphing, but also being able to find the domain and range without graphing is important. So in example 5, we have y equals 3 times x minus 1 to the 1/2 plus 2. Well, what this really is saying is this is really saying y equals 3. That 1/2 is like the square root then of x minus 1 plus 2. And what we're going to do is we're going to, in our table, we're going to ignore h and k. So this is what we're going to make our table. And notice I even gave you a clue here. It's not all of y, it's everything ignoring h and k. And because we're ignoring h and k, we can use our old friends, 0, 1, 4, and 9 in that table. Again, ignore this h and k. So let's just substitute it in here. The square root of 0 is 0, times 3 is 0. The square root of 1 is 1, times 3 is 3. The square root of 4 is 2, times 3 is 6. The square root of 9 is 3, times 3 is 9. So what we could do is lightly plot these points, 0, 0, 1, 3, 6, 9, 9 is way out here. But we can see the shape that it's going to take. And we're going to do this either very lightly or, okay, because this is not the actual graph. This is still step 1. This is just our table. What we actually want to do, however, is we actually want to graph this function, which means what we need to do is now this tells me to move the graph a certain way. This tells me to move the graph right 1 and up 2. So I'm going to take every one of these points and move it right 1 and up 2. And I would do this in another color. Right 1, up 2. Right 1, up 2. And those are the points that I'm going to connect for my final graph. And I need to make sure that this one is either darker or something, that this one is our final graph. So it should be coded. It should be very evident which one your final graph is. I like seeing both the parent and the other graph. I cannot make you do that, but you have to have the final graph on there. My kids that don't put the original graph get it wrong more often than those that do. So please follow that suggestion. And that's the graph. So then let's think about what we could do for the domain. Okay? Is there a domain restriction? Yes. So we look at the original function, what was under the radical. And what was under the radical was we had x minus 1 under the radical. We want what's under the radical to be greater than or equal to 0. How could you solve that? You could add 1 to both sides, and you get that x is greater than or equal to 1. And that's my domain. What about our range? Remember, we're going to compare y to k. What was our k here? Our k was 2. So to decide if it's greater than or equal to 2 or less than or equal to 2, we look at a. And we notice that a is positive. Since a is positive, that means that it's going to be going up as we visually see. So y is going to be greater than or equal to 2. And that's our range. And now I think we're ready to compare using RST. So when we look here, R would be a reflection. I don't see that since A is positive. S, well, the absolute value of A is greater than 1, so that indicates we're going to have a vertical stretch by a factor of 3. And then the translation is the way we translated our table. What we did is we translated right 1 and up 2. And that's how we can do translated graphs. Let's try the same thing in example 6. In example 6, we have y equals negative 2 times x minus 3 to the 1/3 minus 2. Well, again, for some of us, maybe it would be easier to write it in the radical. And what's in the radical is x minus 3. So I have negative 2 times the cube root of x minus 3 minus 2. Now, in our table, once again, we're going to ignore the h and the k. None of that. We don't want that because we want it to be nice and easy. And when we deal with the cube root functions, what were the numbers we said we wanted to put in for the cube root? We said in for the cube root that we should put negative 8, negative 1, 0, 1, and 8. Let's try to put those in, and hopefully it'll be a really easy table for us to make. So let's start by putting negative 8 in. Again, we're ignoring h and k. So if I put negative 8 in, the cube root of negative 8 is negative 2 times negative 2 is positive 4. The cube root of negative 1 is negative 1 times negative 2 is positive 2. The cube root of 0 is 0 times negative 2 is 0. The cube root of 1 is 1 times negative 2, which is negative 2. The cube root of 8 is 2 times negative 2 is negative 4. That's how easy the table should be to fill in, you guys, all right? So you should really have those cube roots down pat, and it makes it really easy. So I'm going to plot these points. Notice that this scale is going by 2's instead. So just be careful when you're plotting. Negative 2, 4, 6, 8, 4. So negative 1 is going to be halfway between here. So just pay attention to the scale on the graphs. And we plot these points on the graph, and remember that this is not the final graph, so this is going to be very light. To get our final graph, we're going to have to use this translation here. This translation here, this minus 3 under the radical, tells me I need to go right 3, and the minus 2 on the outside says to go down 2. Now be careful, because right 3 isn't 3 boxes, because each box is 2. So I need to go right 3 units. So 1, 2, 3, and then down 2. So it's like I'm going to the right 1.5 boxes and then down 1 box. So again, 1, 2, 3, 1, 2, 1, 2, 3, 1, 2, 2. I'll kind of guess right there. And then I can connect those points. The cube root function will have arrows in both directions. And you should either color code or very clearly label what the final graph is so that we can tell by looking at it what the final graph should be. Okay? And when it asks us for our domain, remember in the cube root we could put anything in we wanted. Our domain is all real numbers. Our range, slowly but surely, it'll get there to all real numbers. Yes, every time you have a cube root function, that's the domain and range. Okay, always all real numbers for the cube root functions. And so then our comparison, our RST, we can look based on the original function. So R, we look at A, and we see that A is negative. So that indicates that there is a reflection in the x-axis. And if you look at the picture of the parent function and compare it to this guy, you can see that they're facing in opposite ways. Next, S. We take the absolute value of A. We'll notice that's greater than 1, so that's going to be a vertical stretch by a factor of 2. Next, we use the same translation that we did with the table. We took our table and we moved everything to the right 3 and down 2. And so we'll talk about that here, that we translate to the right 3 and down 2. And that's our comparison. So I do want us to be able to look at functions and be able to tell what the domain and range is if we have to deal with any restrictions, etc. So we'll practice that in example 7. First thing, we have to decide if there are any restrictions on domain and range. In this one, it's a square root function, which means there is going to be a restriction. And we said that what we do is we take the radicand and we set it greater than or equal to 0. That's all we do anytime for the square root function. Take the radical greater than or equal to 0. And so what that means is that our domain is x is greater than or equal to -3. That's it. For our range, remember we're always going to compare y to k. My k here is 2. And we have to decide if y is going to be greater than or equal to 2 or less than or equal to 2. And to decide, we look at a. Notice that my a is negative. Because a is negative, there's going to be a reflection and the graph is going to be going down instead. So that means that which inequality symbol should we choose? The less than or equal to sign. And that's your range. If we were to do the comparison, which I'll kind of rush through because I feel like you guys are good with that. Again, the negative for A means that there is a reflection in the x-axis. S, I also look at the A value, and I see that the absolute value is less than 1, which means that there's a vertical shrink by a factor of half. And T is the translation, so I look at my H and K, and I see that this would be a translation left 3 and up 2. So just like before, the H is the opposite of what you see, but the K is the same. Okay? Next one, yay! Example 8, we have this cube root function. For cube roots, do we have any domain restrictions? We don't. We don't have to worry about any domain restrictions in the cube root. So our domain is all real numbers. And what about our range? That's right, that's all real numbers also. So you only have to worry about having a different domain and range in those square root functions for this section. In our comparison, RST, R, our A value is positive, so there's no reflection. S, the absolute value of A is greater than 1, so that's a vertical stretch. And T, let's see, there's nothing underneath, so it's not moving right or left, but this +2 on the end means I'm going to translate this up 2. And there you have it. Now, one thing real quick, you guys, on the notes, when we were graphing, we made sure that, like, for all the square root ones, there are 4, and all the cube root ones, there are 5. On the homework, though, I think we deliberately put 5 on each one because we want you to be able to think about when it's appropriate to use that. So there might be extra pieces. So if that's the case on your worksheet, just cross off the extra piece. So if this was a square root one that had 5, then just don't worry about that last piece. I mean, if you really wanted, you could fill in 16, whatever, okay? But yes, it was deliberate that there are 5 boxes on every problem on the homework worksheet, okay? This would be on the non-calculator part, by the way. Okay? All right, thanks, guys. Have a great day.